Hello everyone and welcome back to a new video. In this video, we are diving into an exciting and practical application of deep learning, which will be object detection on satellite imagery and coordinate extraction. In this comprehensive tutorial, we are going to cover the entire pipeline from how to download the label data using the amazing RoboFlow universe, then training a powerful YOLO V11 model in Google Colab. Also, we're going to see the crucial step of converting our pixel-based detections into real-world geographic coordinates, latitude and longitude. And finally, visualizing our detections as an interactive layer on a map. So this isn't just theory, we are building a practical solution. So let's start the video. I am using Google Colab. I'll provide this link in description section so you can directly access this Google Colab. So I'll just connect the GPU. So I'm connecting the GPU here. Because we are using a deep learning model, so it is always better to run the models on GPU, not on CPU. So our notebook has been successfully connected. Now I will install the necessary libraries. It may take some minutes. And importing the necessary libraries. So here in this code block, you can see I'm directly downloading the RoboFlow datasets. So I'll show you how you can download this data from RoboFlow. So for that, go to RoboFlow website. I'll provide this website link in description section. You can directly go to this datasets. And here you can see in the right hand side, right hand top corner, download dataset. So just click on that. Then here the option will be download dataset. Then continue. Since we will train YOLO V11 model, so I have selected here YOLO V11. You can choose accordingly. If you want to train a V8 or V9 model, you can select accordingly. Here two options are there. One is download zip to computer. If you want to run the model or train the model on your local PC, you can download this. Else, the second option will be better. Just show download code and continue. It will show small code, and you can see this code I have pasted here. You can directly go copy this code and paste in the notebook and run the cell. It will automatically download the datasets. And before that, also make sure that you have installed the RoboFlow library. Otherwise, this code will not run. Okay. So I'll quickly download the dataset. Okay. Our datasets has been downloaded. You can see here, test, train, valid. So these are already labeled datasets. We do not have to do any labeling because in this RoboFlow universe, there are millions of datasets which are openly available, and we can download and use those datasets directly. I recommend you can download datasets from here, but for production level or very high accurate tasks, you need to do your own labeling. These datasets are not that much accurate. So for this demonstration, I'll quickly download from here and show you. So our datasets has been downloaded. Now we just quickly change this data.uia.ml file. Unnecessary information we'll remove from here. We don't need this test. We need the train and images folder path. Copy the path and paste here. Similarly, we need validation image folder path. So our YAML file has been uh, updated. After changing the YAML file, you can directly go for training. So here in this code block, you can see I am loading the YOLO V11N model. Because this is just a tutorial, I'm using nano model. For your own task, you can use medium or some large YOLO V11 models. But for now, I'm using N. Then here the simple code for YOLO training. It's a very easy or one-line code. This model.train. Then you have to paste the YAML file path. Then some hyperparameters tuning. I'm using very simple hyperparameters here. I'm keeping epochs only 50 and the default image size is 640. You can also add the batch size, then other so many parameters are there in hyperparameters. So you can add those as well. But for easiness, I'm keeping this only and I'll start training now. The training started. It will take some time to train. So you can see the first epoch is running. Till now, if you find this video is helpful for you, then please do subscribe and like this video and comment if you want some related videos or some theory part that I need to cover. So you can comment down below. Meanwhile, I'll fast forward this training part. Model training has been successfully completed. So you can see these are the results and it's showing our results stored inside this directory. And these datasets are having this many of classes like camping car, other pickup and truck and van. So here you can see the summary of the training. So for each classes, there are some certain scores like box precision, recall, map score 50, map score 50 to 95. Because of the data sets or some other hyperparameters, the model may be less accurate, but the process that I'm going to show you here, that is more important. Like you will input a geotiff image and the model will detect the object and then we will convert that normal bounding box coordinate to exact latitude longitude plottable coordinates. So that will be whole process. Now in the next code block we need to paste the trained model path. So for that we need to copy the path of the trained model and paste here, as well as the image path. For the image, the images that we have used for training, those are normal JPG image and do not have any coordinate information. But we need a image which has coordinate information and it is georeferenced. So we can extract the coordinates of that, of detected objects. So for that, I have uploaded this test data.tiff. I'll provide this image link. You can directly download and upload it here. Then simply copy the path and paste here. I'll try to reduce the confidence score because maybe only 50 pox accuracy will be less. So maybe 15, 0.15. This is very less, but that's not important. You can see it can detect some of the cars. Now, our main task is to extract the coordinates of these bounding boxes that you can see that white bounding boxes. Currently, these are normal pixel coordinates, not georeference coordinates. We will perform the coordinate extraction methodology. I will quickly explain you about the methodology that we're going to use here. So to convert the object detection coordinates into plottable latitude and longitude, we follow a three-step process rooted in the data embedded within GeoTIFF files. First, the normalized coordinates are scaled up by the image pixel width and height to find the precise pixel location of the object on the image grid. Second, we use the GeoTIFF's internal affine transformation, that is a built-in geometric rule to map those pixel coordinates into real-world coordinates, and it is often used in meters like UTM. Finally, if those coordinates are not already in WGS 84, which is a global standard for latitude longitude, we perform a mathematical reprojection to translate the meter-based coordinates into the familiar degree of latitude and longitude, which are then saved into GeoJSON file. In this simple diagram, you can see this is a input image which is georeferenced. I'm using this image as our input to YOLO model, and the YOLO model is giving a output with detected bounding box. So we have the x and y coordinates of these corners, which is in a simple normal coordinates, not the georeference coordinates. So we have the normal coordinate information, detected objects coordinate information. Now we will use this coordinate information to to extract the exact latitude longitude information from the GeoTIFF file. So you can see the methodology simply is the yellow model is giving us the output with bounding box coordinate, and using this bounding box coordinate we are extracting the latitude longitude information from the input GeoTIFF image, because the output image do not have any GeoTIFF information. By default, whenever you input a GeoTIFF georeferenced image into yellow model, it will give you output as a PNG, which is not georeference. So model automatically erase all the georeference information and all. So this methodology we need to follow. It is possible there are some other methodologies as well, but in this video I'm gonna use this methodology. In the next code block, here I'm defining image path, then trained model path, then also output path here, then the confidence threshold. I should reduce this to 1.5, otherwise the detection will not that much good. In this Python function, our model will take a input image and detect the target objects. Also, it will collect the detected objects bounding boxes, which will be normal bounding box coordinate, and those normal bounding box coordinate will be used to extract the exact latitude longitude information from the input image. Simply I'll run this code blocks. So it is the process has been completed successfully. Then I will save the detected bounding box coordinate to GeoJSON file. GeoJSON file is very useful when we will plot this information to a web application. So here in this Python function, we are simply converting those exact coordinate information to a GeoJSON file, and we are saving that GeoJSON file. So I'll run this. So you can see our GeoJSON file has been saved successfully. Now we will plot this GeoJSON file on a map. So for that, I'm using a Folium library. It is a Python library. Using this Folium library, you can plot different datasets, GIS datasets, especially vector datasets on map, and you can visualize and you can do some analysis. So I'll run this code. So you can see how we have successfully extracted the coordinate information, and we have also successfully plotted it on the map. So I think you have understood the whole process. This was just a simple process. So if you learned a new thing, please like the video and subscribe my channel. Also, please share the video to your friends and in your college group and your personal GIS group. Thank you everyone.